Um, it's been a while since my last recording. Um, I've built some inversion codes based upon sw4. Um, but for people who are familiar with our previous work, um, you probably know that we also have a inversion code that's built on top of the inelastic wave propagation or AWP code. In fact, the book that I wrote with Henry called Full 3D Seismic Waveform Inversion, published by Springer, was actually based upon that for the simulation code. And we have a huge code base that actually do full 3D waveform inversion based upon just the AWP code. The AWP code is a uniform mesh staggered grid, fourth order staggered grid final difference code. So um, it doesn't account for topography, it doesn't account for um, variable mesh, right? You can only use like a one mesh with a constant grid spacing. So we used that for the simulation code in our work for Southern California, the crustal tomography that Henry did his PhD thesis on. So we have a quite extensive code base based upon AWP. And what I have been trying to do since my last recording was to actually integrate that part of the code, that part of the inversion code, together with the inversion code that we have built on top of sw4. So, so what I have been trying to do is to actually create a code base for full 3D waveform tomography based upon either AWP or sw4, based upon your choice. Right? sw4 is more capable. It allows you to use multiple composite grids with different grid spacing, and it also accounts for topography by using curvilinear grids on the top of the modeling volume. And but the advantage of AWP is that it's still faster. So uh, if you uh, if you run the same kind of simulation, for example, the half space example that we have been using for computing the grids, AWP can actually finish in like a much shorter amount of time using on the same number of CPU cores. So AWP is still faster than sw4, but sw4 is more capable than AWP. And eventually, what I will try to do is to actually integrate the inversion code based upon uh, discontinuous lurking method. We also have a separate code for doing full wave inversions based upon the discontinuous lurking code called sw4. And that's for now it's a separate code, right? But eventually we're gonna integrate that code into the same code base. So eventually our inversion code will be able to actually utilize three different wave propagation simulation codes. Two of them are going to be finite difference. One is AWP, the other one is sw4, and one of them is going to be based upon the discontinuous clocking or the SISO code. Um, but for now, let's look at my progress. The progress I've made so far to integrate the inversion codes based upon AWP and um, sw4, right? So here it's on Teton. So that's the new cluster uh, at University of Wyoming. So um, our code is still called F3DWI, and then the the code directory is slightly different now. So AWP, if you look at the AWP, it's got its own source code. This part of the source code actually includes the forward simulation code that's associated with the AWP code. Lots of those Fortran.f files were actually coming from the AWP source code. And then there was a bunch of .f90 and then .c. Those files were actually inversion codes based upon AWP, right? And then if you look at sw4, it's got its own source code, right? It's got its own source code. That was the source code I've been using in this particular video series to show how to compute kernels using sw4. Um, and then inside of sw4, we also have a directory for the source code of sw4, right? That's the full simulation code that you can download from GitHub, right? The only thing is that inside of the source directory of sw4, there are some changes I've made in order to actually make it compatible with my inversion codes, right? And most of the changes are um, actually inside of the file called sw4.c, right? Most of the changes. So the changes I've made are delineated or indicated using / poll. So all those changes are made by myself to make it compatible with my inversion codes. Right. And then there's also some other changes I've made throughout the source codes. Um, uh, I cannot actually, if I just do a grep -- poll star, I should be able to. Oh, sorry. Um, then, okay, I also made changes in the ew.c file. Some changes in the geographic projection file, and then the file for reading the inputs to sw4, and then yeah, so that's pretty much all the changes I've made, I guess. Um, but now the integrated source code is underneath f3dwi now. It's not inside of the awp or sw4 subdirectories. It's inside of the src directory that's directly underneath f3dwi. So if you look into src, then you've got a bunch of source codes that's that's written to actually integrate the inversion codes based upon AWP and also SW4. Um, yeah, that's how the source code are organized for now, right? Um, so this is on Teton. I should have a mirror image of all the source files um, on my home machine. That's at Pochen full wave, right? So the codes were developed using VS Code. So VS Code allows me to actually do this kind of editing quite easily across different platforms. Um, so uh, let me see. So on my home machine, it's supposed to be underneath GV0 brick F3DWI, right? So underneath this particular directory, I should also have a source directory, and then all the files, all the source codes um, here. Underneath this directory should be a mirror image of the source codes on Teton underneath this particular directory. So they should be synced. They should be synced. For now, it's not automatic, but the sync should be done automatically. It's um, yeah, and then the binaries are supposed to be inside of Bing, inside of the Bing directory, directly underneath the f3dwi directory. So if I look into Bing, I should have a bunch of binaries over there, right? Um, yeah, that's how the source codes are organized and how the binaries are organized. So all the binaries are gonna have like just 3 letters. The name of all the binary files are gonna just have like 3 letters. Right? Box is the binary for generating for creating a simulation box. Right? Inside of this box, we are gonna do our inversions. We are gonna do our simulations. So this box is gonna be the entry code, right? Um, So for different kind of configurations, for example, AWP actually uses some kind of input that requires you to enter the four corners or the first two corners, um, of the box, right? The, the longitude, latitude, and then the the length of the y-axis, right? The length of the x-axis, right? And then the thickness of the volume. And then sw4 can actually use a kind of variety of inputs. You can specify the UTM of the four corners. You can specify 2 points at the center of the box, right? And then um, there are different ways for specifying the box. So once the box is set up, then the coordinate system and also the coordinate transforms um, that's needed in order to actually convert vectors and tensors um, uh, back and forth between the box coordinates and the uh, east-north coordinates, and can be performed. And then we've got a URG, that's for uniform recording grid. So in order to actually do the simulations, in order to actually do the inversions, we have to record the strain fields um, at a subset of recording grids, which the recording grids is a subset of the simulation grid. Uh, it's a decimated version. It's a uniformly decimated version of the simulation grid. So so in order to actually create that kind of a recording grid, so the simulation, when we do wave forward simulations, so we can record the strain fields, we have to run this code. And then RG is for random recording grid. So sometimes we don't want the recording grid to be kind of a uniform, right? Uniform recording grid is just for tomography inversions, but for example, for source inversions, we may have to actually record the strain fields at some random locations that's kind of distributed throughout the entire volume, and they may not have exactly a kind of a structure to it. So this kind of random recording grid has to be created using RRG. And then we have WPS. It's called right point source. So this code is only used by uh, AWP for now, right? So this is for preparing the source input file that's going to be used by AWP. For sw4, the source input file is actually integrated together with the entire simulation input file. So there's no separate source input file. So for now, WPS doesn't actually. Uh, so sw4 doesn't. For inversions using sw4 doesn't. We don't really need WPS for now. But later on, um, once we have uh, um, but later on we may have to, so we may add some capabilities to WPS so that we can actually automatically create the source line into the SWP input file, the line for specifying the source. And then the next one is called a pre. That's for pre-calculation or pre-simulation. So this pre again is used by AWP for now, right? For SW4 it doesn't actually have any kind of effect. Um, this is for setting up the directories, the directory structure for storing the strain fields, for storing the different kinds of strain fields, and then the outputs, right? The outputs of the AWP simulations, and then uh, creating the correct directory structure, and then copy over all the correct files that's generally previously by using other codes, right? R2S is RGT to synthetic, so basically reads the receiver green tensor files and then creates synthetic algorithms. And then there's gonna be a bunch of other binaries. They are all gonna be like 3 characters or 3 letters, and but for now, that's all the binaries that I've created so far. So let's look at how we can actually use the same code base to actually run AWP, right? So So let's go to G scratch. That's my work directory, pchan, right? And then kernel examples, right? And then so for now, there's the directory inside of the kernel examples are organized like different kind of a model, right? In the past, it was organized into like two subdirectories, AWP and sw4, and then inside of each subdirectory, we have different models or different kind of examples, right? But now now the code is organized as the examples are going to be sort of the first level subdirectory, and then inside of the first level, say HS half space example, we're going to see two directories, AWP and sw4, right? So if I go into AWP, we're going to see the familiar directory structure called jobs, FWF, and VM, right? Um, so if I go into jobs of AWP code, the AWP directory, then I'm gonna see SR info, right? SR info is gonna have a bunch of input files for describing the different sources. The most important file inside of this particular SR info directory is the SRLST, SR list, right? So the format of this particular file is identical to the one that's described in the book. Um, um, it can be used for describing point sources, and then it can also be used for describing non-point sources, right? Extended sources that's composed of multiple point sources with different source time functions, that kind of thing. So it's quite a flexible format, um, and this file is just a list of all the sources, and also including receivers, right? Because receivers can be used as a source when we compute Green's tensors. Um, that's the most important source file, right? And then this file has to be created by hand. It's not automatically created. You have to, at least for now, there's no graphic user interface for you to actually create this kind of file automatically or something by click and drag. You have to sort of edit this particular file using a text editor, not Word, not Excel, not any kind of a. It has to be a text editor on a Linux operating system. That's one of the most important input files that we have to create by hand. And then there's another input file that has to be created by hand. That's this file. That's the control file for inversions. It's not too long, but it's got a certain kind of format. Again, the format is identical to the one described in the book, so I'm not gonna sort of repeat everything that's already in the book. But basically, it's just the format of this file is basically just specifying a bunch of configurations, telling the code or telling the code where all the different directories are, right? And then some of the basic simulation examples. The format has to be um, using this equal sign, right? Some parameter equals to something. So it's key value pair, right? It's a key value pair, lots of key value pairs, and the key and value has to be separated by a equal sign, right? This space is optional. It doesn't have to have spaces, but the equal sign has to be there. So otherwise, the code won't be able to actually recognize it. And the ordering of the different key value pairs doesn't have to be following this particular example. It can be kind of random. It doesn't have to be following this particular example. So two of the most important lines. One is where the material property files are going to be stored, right? That's the velocity model, right? And then the other one is the source receiver line, source receiver list, the complete path to the source receiver list file. And then here we have UTM zone, because AWP is going to, very likely AWP is going to be using UTM as a projection. And you have to specify the zone, UTM zone, right? So for this particular example, I was using UTM zone equals to 11, right? And then for URG, the uniform recording grid, these three lines are kind of useful, right? How many grid points you want to skip? That's the decimation rate in the x, y, and z directions. Yeah, that's all the important things, I guess. Right. That's the second file that we have to actually create by hand. And then there's a third file that we have to create by hand. That's this particular file, mesh.in, msh.in. You can name it in any way. The file doesn't have to be named in this particular way. But again, the input file, the format of this input file is kind of identical to the one described in the book, right? Longitude, latitude of the first point of the box, the second point, right? And then the length of the x-axis, the length of the box along the x-axis, and then the thickness of the simulation box, and then grid spacing, and then how do you want to partition the entire mesh into like different chunks so it can run in parallel. Um, for now, there's some kind of redundant information, right? Because this line where the velocity model is going to be stored is actually identical to the one in the parameter file, right? And then the UTM zone 11 is also identical to the one that's uh, that's um, that's in the parameter file, right? But for now, we don't have to worry too much about it. Later on, I may have to change the code to actually remove this kind of redundancy. Or just to try to combine these two files into like one file, right? Maybe that's a good idea, right? Maybe I should just combine the mesh.in input together with the parameter file, so that later on we don't have to actually sort of look at two different files in order to actually um, to initiate all the calculations, right? So yeah, I think I'm gonna do that later on, right? Yeah, that's all the files that has to be created manually, and uh, and if I want to create the box, all I have to do is to run box, right, and then just use msh.in as the input, and then it's gonna run, and then it's gonna create a very important file called xyz.xyzgrd, and this file is gonna be stored inside of the velocity model directory, right? It's gonna be this particular file, and this particular file actually. Um, This particular file actually describes the grids and then the UTMs of the four different corners, right? And then lots of the remaining simulation codes, inversion and simulation codes are going to use this particular file. And then the next thing that I have to do is to actually create the velocity model for each of the chunk used in the simulation. So here we have 4 times 4 times 4. That's like 4 chunks in the x direction, 4 chunks in the y direction, and 4 chunks in the z direction. So that's like a 64 files. We have to actually create a 64 files for the different parts of the velocity model. Um, and then this part is actually identical to the book. Um, we have this particular very simple code for creating a uniform mesh, uniform velocity model. So the code is kind of very simple, right? All we have to do is to actually specify the correct path, right? So this C++ code is not very well written, but it actually serves the purpose. All those numbers has to be actually hardwired. It's hardwired. You have to sort of manually change them before actually run this code, right? It has to be changed. These two lines has to be changed to actually to be consistent with actually the information in the XYZ file. So, but this code is just for generating a uniform half-space structure model. For much more complicated, for example, a three-dimensional structure model, this code will have to be changed substantially. In the past, we have been using just a MATLAB code, MATLAB scripts to actually generate the velocity model. The code is not so difficult to written. All you have to do is to worry about how to actually convert the grid index to a global grid index into a local grid index, that kind of thing. But the calculation is kind of very simple. So once you finish compiling this code and then run this code, you're gonna see all the HSGRD files. These files are for half-space velocity model. They are pretty much storing exactly the same kind of information. It's VPVS and density at every grid point, and they are constant. They don't really change with space. And then once you got those files, the next thing you want to do is to actually run the URG code, the uniform recording grid, right? So the uniform recording grid bin URG, right? The uniform recording grid file is gonna take the parameter file as the input, right? And then once you have finished running this uniform recording grid code, it's gonna create the recording grid for it's these kind of files, right? These are all just ASCII files, text files. One of the very important difference between AWP and sw4 is that these kind of for AWP, all those recording grid files are actually storing the grid index in the local coordinates, right? So you can sort of see. So this is a chunk that's maybe I should try something else, right? Let me do a head of some other file somewhere, right? So you can sort of see the the grid index starts from like a 1, right? If it's global index, it cannot be 1, right? Because this is the chunk that's like not the first chunk. It's some chunk at the not close, not exactly located at the origin. So all those grid indexes are actually local. They are local. They are local grid indexes, right? This is different from AWP. So if you look at something that's in the AWP direction, different from sw4. If you look at the files in the no, it's yeah, GRD REC. Suppose you look at some other files, right? They don't start with except for the z coordinate, because the sw4 code doesn't actually partition the grid in the vertical direction. So every chunk is gonna include all the different z grid, right? Um, but AWP actually partitions along the z direction, so not every chunk actually starts from the contains all the z grid. Um, but here you can sort of see that the grid index here, they are actually a global grid index. It's not local grid index. It's global, right? It's referenced to the origin of the entire grid, right? This is one of the very important differences that we have to actually pay attention to, right? Because later on, once we have finished calculating the kernels on each of the different grid and try to actually assemble all the kernels on different chunks into like a one grid, uh, this kind of a thing has to be accounted for, right? This kind of difference has to be accounted for between AWP and sw4. So that's one of the very important differences. Um, Let me still go back to the AWP code, and then that's that's UR, uniform recording grid, right? And then the next thing that we have to do is to actually create the random recording grid. For now, the random recording grid is actually created based upon the source receiver list. So every point that's used in the source receiver list file are going to be used as the center of some kind of stencil grid. And the size of the stencil is actually controlled by the parameters in the parameter file. 1 in x, 1 in y, and 2 in z. So in the x direction, the stencil is going to be like one grid point on either side, and then on y direction, it's going to be one grid point on either side, and then in the z direction, it's going to be two grid points up and down. Right, that's going to be the stencil size. And then this is just for source inversions. Later on, if we want to use invert for example CMT, the moment handler, those kind of things becomes useful. So all we have to do is to run RRG, right, and then use parameter file as the input, and then it's gonna create a bunch of files that looks like that kind of thing, called HSGRDRECRDM random, right, and the format of these files are kind of similar to the format of those uniform recording grid files, except that those the grid points inside of those files are not exactly organized based upon a uniform spacing. And then after that, we have to do one more thing, which is actually write the point source, right? So all we have to do is to WPS, right point source. So for now, there's inside of the FWF directory, we have those those inputs already, those directory structure built up already, right? Uh, for example, all the links are there, right? And then the output directories for storing the check files and also for the string field volumes, right? That kind of thing. And then this particular file, this source file used by AWP, this file has to be created, right? And we can create it by using WPS, right? And then this time the input command line input is slightly more. It's the parameter file, right? And then what we have to do is to specify the starting and the ending line number in the source receiver list. So if we do look at the SR info, SR LST, if we look at this particular file, we have for now 1, 2, 3, 4, 5, 6, 7, 7 lines, right? 7 lines. But every line that's gonna start with that's starting with a 0 is gonna be skipped, right? Those are not exactly source or we want to run simulations on. These are just some recording grids, some grid points that we have where we have receivers or we want to actually know some grid information, that kind of thing, right? We have to specify the starting and ending index, right? Because sometimes we may not want to do simulations for every line in this source receiver list. So if that's the case, um, we have to uh, uh, we have to specify the starting and ending line number. So here I'm not gonna sort of do just a partial. I'm gonna use the entire list, starting from the first line 1 and then end with the last line 7. Right? And then it's gonna create all the .src files in each of the directory, and it's also gonna create the directory structure. It's also gonna create some of the directory structures. Right? If the source directory doesn't exist underneath FWF, it's gonna create it. Right? And then the last thing that we have to do is to actually run the run pre, right? Pre, and then parameter, and then again we have to specify the source and receiver range. And this code is gonna try to actually create all the different directory structures and uh, make sure all the input files are there. And if there's any kind of problem, it's gonna report it. And for now, that's all the preparation that needs to be done for running AWP, right? And then once all the input files are prepared, one of the very important input files for AWP is actually called in3D, right? So in addition to this source file, there's another input file called in3D, and this in3D is also needed by AWP. And this in3D file was created by using this this pre, this file, this binary, right? So um, So once that's done, we can actually go into the different source directory and then create a link, create a soft link that's going to point to the actual binary of AWP, and then create a job script, right? So create a job script and then just submit to the job script, right? So for now, the simulation actually requires 64 cores, right? So on Teton, every node has like 32 cores, so all I need is like 2 nodes to run the entire thing. And the simulation is supposed to be finishing like just like 2 minutes or something, right? Um, yeah, uh, less than 2 minutes. It's 82 seconds, right? Just 1.5 minutes to actually finish the half space simulation. So yeah, that's how the code is actually set up to prepare all the input files that's going to be needed um, by AWP, right? And then once the simulation is done, all the output stream volumes will have to be uh, uh, used to actually compute the kernels, right? And we have to actually um, modify the code for kernel calculations to actually read the output of AWP, right? and then um, we can have a complete code for integrating together AWP and sw4.